Welcome back. Let me start by reviewing the idea of the tangent plane and the normal vector to tangent planes. So let's say that S is a surface. That's the graph of the equation g of xyz equal to 0. So we can think of S as the level surface of the function g. So here, let's say that P is a point on the surface S, and then let's pick a curve C lying on the surface and passing through the point P. Let's say the out of t is a vector function that parameterizes C, and P is the value of R at the input t naught. At the input t naught. Recall that the R prime of t naught will be a vector tangent to C at the point P. Now, if we look at g of out of t being a point on the surface, it must satisfy the equation g of xyz equal to 0. So g of out of t would be 0. And if I take the derivative, then we get the gradient of g evaluated at out of t dot product with r prime of t is equal to 0. Now, if we replace t by t naught, then out of t naught would be p, and r prime of t naught would be right here. So we see that the gradient of g at p is perpendicular to the tangent vector to the curve C at the point P. So, and this is true for any curve. So no matter what curve we pick passing through, no matter what curve on the surface we pick through P, the gradient of g at P will be perpendicular to that curve. So basically the gradient of g at P is perpendicular to the tangent plane, is perpendicular to the tangent plane at the point P. So now let's say that we want to find the extremum of the function f of xyz subject to the constraint g of xyz equal to 0. So basically then the graph of g of xyz equal to 0 is going to be a surface, and I'm calling that S, and that's, again, you can think of that as the level surface of g, of the function g. And basically we are restricting the domain of f to this surface S, and we want to find the maximum and minimum of f on the surface S. And so again, we want to find the extremum of f subject to the constraint g of xyz equal to 0, and what I'm going to assume is that the extremum of f occurs at some point denoted by P. So I'm assuming that the extremum of f occurs at P. Then we know already that the gradient of g at P is perpendicular to the surface at P. That is, it is perpendicular to the tangent plane to the surface at the point P. Now I'm going to show you that the gradient of the function f will also be perpendicular to the surface at P. Now, the gradient of g is actually perpendicular to the surface S at any point. The gradient of g is perpendicular to the surface at any point. But if the extremum of f occurs at p, only then the gradient of f will be perpendicular to the surface at p. So let's check that. So f of xyz, we are considering f of xyz subject to the constraint equation g of xyz equal to 0. Now, so S is the graph of this constraint equation, and so let's let C be a curve on the surface passing through the point P. Let's say R of t is a parameterization of C, and R of t naught is P. R prime of t naught is a tangent vector to the curve, to the path C at the point P. Now, if so notice that so we know that the extremum of S, we are assuming that the extremum of F occurs at the point P. Now, if we look at the function f restricted to the curve C, then we can look at the following function. So if I look at f of r of t, right, r of t is r of t varies over the points on the curve C as t varies. So by looking at the function f of r of t, we are looking at the function f restricted to the domain C. So if f has a extremum at p, then f of r of t has an extremum at p as well, and then the derivative of f of r of t at t naught will be 0. Because if f of r of t has an extremum at p, which is equal to r of t naught, that means that f has a critical point at t naught. Sorry, f of r of t has a critical point at t naught, and therefore the derivative of f of r of t at t naught should be 0. And then we see that the gradient of f at p, dot product with r prime of t, would be 0. And then if because we are evaluating the derivative at t naught, we get the gradient of f at p dot product with r prime of t naught is equal to 0. And so if f has an extremum at p, then we see that the gradient of f at p is also perpendicular to the surface S at the point P. So we already know that the gradient of gradient of G is perpendicular to the surface at P, and we now found gradient of F is perpendicular to the surface at P, so they must be parallel. So the gradient of f at p is a scalar multiple of the gradient of g at p. So lambda here is a scalar. So in my discussion here, we require that f and g are continuously differentiable in an open set containing the surface S. So once again, we are trying to find the extreme values of f subject to the constraint equation g of xyz equal to 0. And what we have found is that if f has an extremum at the point P on the I should be saying on the surface g of xyz equal to 0, then P satisfies the equation that the gradient of f at p is a scalar multiple of the gradient of g at p. And so once again, let me emphasize that the surface S is the graph of the constraint equation, and the gradient of g is perpendicular to the surface at any point on the surface, whereas the gradient of f is perpendicular to the surface only at the point P where f has an extremum. That's what we have shown. So to find the extreme values, then we have to solve the system of equations. Gradient of f is equal to lambda times the gradient of g, and g of xyz equal to 0. And the first equation here can be the first equation here actually gives us three equations, that the partial of f with respect to x is lambda times partial of g with respect to x. Partial of f with respect to y is lambda times the partial of g with respect to y. Partial of f with respect to z is equal to lambda times partial of g with respect to z. And then the last one is the constraint equation. So if we solve this system of equations, then we're going to find the points. We solve this system of equations to identify the points P where the extreme values may occur. Okay. So let me stop here, and in the next video we will be looking at the Lagrangian.